Our next lesson is called Solution Sets of Linear Equations in Two Variables. We're going to start with an opening exercise. I'd like you to pause the video and try the following question. What is the solution set to the following equations, part A and part B? So again, at this time, pause the video, try these two questions, and then resume the video to go over the answers. Okay, so at this point, you've had a chance to try the opening exercise, so let's go over the answers. In letter A, this should feel very familiar to you. You are solving an equation that has one variable in it, x. So you are adding 18 to both sides, then dividing by 4 to get an answer of x equals 7. However, when you try to do that with the equation in part B, this has two variables. So the value of x is going to depend on the value of y. So for example, if I put a 15 in y's spot, 4x minus 15 equals 10, will have a different x value than if I were to replace y with 18 and have 4x minus 18 equals 10. So this is leading us into discussing what it looks like when you have a linear equation in two variables. So if you need to, pause the video in order to fill in this response and then resume when you're ready to move on. Okay, so now let's move on to our investigation. In part A, I need you to circle all the ordered pairs x, y that are solutions to the equation, and we are going to use the same equation that we used in our opening exercise, which is the 4x minus y equals 10. Okay, so at this time, I'd like you to pause the video again and circle all the ordered pairs that you believe are solutions to that equation. When you're ready to check the answers, you can resume the video. Okay, now that you've had a chance to try part A, let's go over the answers. You should have the coordinates 3, 2, -1, -14, 1, -6, 5, 10, and 0, -10 circled. So now in part B, they'd like us to graph the equation 4x minus y equals 10. So in order to do this, let's take our coordinates from part A and organize them in a way that will allow us to use them to make the graph. So we are going to organize our solutions using a table. So we will make an XY table and we'll order our coordinates from least to greatest in this table. So starting with our lowest, which was -1, -14, we then have 0, -10, then 1, -6, then 3, 2, and 5, 10. So now let's go over to the graph and plot these coordinates. Now when I go to plot -1, -14 on the graph that we've been given, that would not fit on the graph. So I'm going to move right to 0, -10. Then 1, -6, then 3, 2, and then 5, 10. And now I can connect these points to make our line. Arrows on both ends. And then we're going to label with the equation. So in part C, how did you decide whether or not an ordered pair was a solution to the equation? Well, the idea in there was that you had a list of options. Each coordinate gives you an x and a y to try in combination. So we want to substitute the coordinate xy into the equation for x minus y equals 10 and see if the equation balances out. Which means essentially we were doing a check. The coordinates gave us an x value and a y value to try in combination. We plugged them into the equation to see if it checks or balances out. If it does, then we know that combination is a solution to our equation in two variables. So in part D, the ordered pairs x, y in the solution set of the equation 4x minus y equals 10 are infinite. What types of numbers then are included in the solution set? Let's circle all that apply. So if they're infinite, we want to think about the different types of numbers we can have. So remember, natural numbers are the same as counting numbers. Did we have natural numbers as part of our solution? We did. We also had whole numbers, which includes 0. We had a value of 0. Integers brings in our negatives. We definitely have those. Now, rational numbers. Is it possible for us to have decimal or fraction combinations that will make this equation true? Yes, there is. Okay. Irrational numbers as well. And real numbers. The only numbers that are not going to be included in these solutions are imaginary numbers, which remember are square roots of negative numbers. So there are an infinite amount of solutions that you can find, which means an infinite amount of combinations that will make this equation true. So as you could see from when we created our graph, let's remember what other details we always need to have in order to complete the graph properly. You always want to make sure you connect the points, that we include arrows, since it is a line, and always label with the equation. So now let's move on to an example that involves a word problem. The sum of two numbers is 8. What are possible numbers? So in part A, we're going to create an equation using two variables to represent the numbers. So since they did not give us a variable, we have to pick a variable and we have to define what it means. Now we are allowed to use two variables since we are now looking at linear equations in two variables. So we will let x equal the first number, and then we'll let y equal the second number. So sum means to add. So we want to take our first number x plus our second number y, and it needs to be equal to a total of 8. In part B, it says list at least 3 solutions to the equation. So we're trying to come up with combinations of numbers that would add up to 8. So some examples would be -1 and 9. If I were to add those two together, I would get 8. I also had 4 and 4. And then I had 8 and 0. Now, are there other combinations? Yes, they just wanted us to only give 3 right now. So those are 3 coordinate combinations of x and y that would make the equation true. In part C, we're going to create a graph that represents the solution set to the equation. How many ordered pairs x, y will be in the solution set? So we'll take our 3 coordinates that we had and organize them in a table like we did before. So I have -1, 9, 4, 4, and 8, 0. So we will plot -1, 9, 4, 4, 8, 0. Remember all the details of the graph that you have to have. So we're going to connect them with a line, arrows on both ends, label the line with the original equation. Now, the second part of the question says, how many ordered pairs will be in the solution set? So as we said before, this is just 3 examples of combinations that would work. We have decimals and fractions or rational numbers and combinations that would also work. So remember, since this line is going on forever in both directions, we have an infinite number of solutions. So there are infinitely many solutions in the solution set. Now in part D, let's say 8 students can be broken into 2 groups. List the possibilities for the sizes of the 2 groups. So let's think of some combinations of students we could have. We'll make it, and again, in an XY table. So we could have 6 and 2. We could have 3 and 5. We could have 1 and 7. Okay? And we could go ahead and plot those points on the graph. 6, 2. 3, 5. 1, 7. Now, usually, I would start to connect these and make a line. But look at the second part of the question. What types of numbers are included in the solution set? Is there an infinite number of solutions? Let's talk about why or why not. So previously, we had no real-world context around the equations that we were graphing. Even in the first example here, we were dealing with just numbers. Now, we know that those numbers are representing different combinations of two groups of students. So are we still working with the same set of numbers? Can we have fractions and decimals and irrational numbers like we did before? No, we can't. So the numbers included here are whole numbers. This is because we are grouping students. So we have real life context now. So that means there is not an infinite amount of solutions. So how does this affect our graph? This means we do not connect the points. So in conclusion, an ordered pair is a solution to a two-variable equation when each number substituted into the corresponding variable makes the equation a true number sentence. All of the solutions to a two-variable equation are called the solution set. Each ordered pair of numbers in the solution set of the equation corresponds to a point on the coordinate plane. The set of all such points in that coordinate plane is called the graph of the equation. And that concludes our lesson on solution sets of linear equations in two variables.